Good day, everyone. Welcome to the week number 13 of our ECA Season 7.1 or Fundamentals of Mixed Signals and Sensors. So for this week, our topic will be multi-rate digital signal processing. Okay. So for the learning outcomes of this week's module, we have number 1, define and understand the concept of digital signal processing, and number 2, be familiar with the applications of digital signal processing. So this will be the topics that we will cover for this module. So we have number 1, decimation and interpolation. Number 2, frequency and transforms of decimated and expanded sequences, sampling rate conversion, multi-stage approach, polyphase filters, and applications of multi-rate digital signal processing. So let's start with decimation. Okay, so decimation can be regarded as the discrete time counterpart of sampling. Okay, whereas in sampling we start with a continuous time signal x of t and convert it to a sequence of samples x of n. Okay, so in decimation and interpolation, we start with a discrete time signal x of n and convert it to another discrete time signal. So this is a discrete time signal to discrete time signal process. Okay, so let's start with decimation. So here we have a block diagram notation of decimation by a factor of m. Okay, so what happens in decimation is that we lower down the sample or the sampling rate of a discrete time signal by a factor of m. So if our signal, original discrete time signal, for example, is x of n with sampling rate of f of s, after decimation, okay, after decimation, we will have this signal y of n, and the sampling rate of y of n is f of s divided by m. Okay, so the sampling rate was divided by a factor of m. Okay, so we have an example here. For example, we have this original signal x of n, original discrete time signal. Okay, as you can see, the sampling rate is high. Okay, so there is a lot of sampling rate samples, a lot of samples because of the high sampling rate. If we decimate this signal, or if we subject the signal to decimation, for example, this is our x of n with sampling rate of f of s, then this one will be f of s over m. Okay, so you can see here, this is 0, this is 3. In between, we have 3 signals from 0 to 3. But after decimation, there is only 1 signal instead of 3. So we have a factor of 3. Okay, so the m here is 3. So we divided the sampling rate of the original discrete time signal by 3. So that is decimation. We lower down the, okay, so we lower down the sampling rate of our signal. Okay. So the block diagram notation of the decimation process is depicted in the figure. So an anti-aliasing digital filter, this one. So an anti-digital aliasing or digital anti-aliasing filter, okay, precedes the downsampler to prevent aliasing from occurring. So last. meeting to discuss about aliasing, and that is due to the lower sampling rate than the Nyquist sample. Okay. The subject of aliasing and decimated signals is covered more in the preceding topics. Okay. So that is decimation. Again, the point of decimation is to lower the sampling rate. Interpolation, on the other hand, is the exact opposite of decimation. It is an information preserving operation in that all samples of x of n are present in the expanded signal y of n. For example, okay, so this is the, for example, this is our x of n. Then we subject this to interpolation. So after interpolation, this will be our signal. Let's call this y of n. Okay. So as you can see, what happens in interpolation is that the sampling rate increases. Okay. In this case, we only have one signal here, but after interpolation, we have 3 samples. Okay. So we multiply the sampling rate of our original signal by a factor of L, that is interpolation. So in this case, we have 1 signal here, and in this case, we have 3. Okay, so 3 over 1, so that is our L. So we multiply our sampling rate f of s by a factor of L. Again, on decimation, our sampling rate f of s is divided by a factor of m. So that's the difference. Okay, again, decimation, lower the sampling rate. Interpolation, increase the sampling rate. Right. So the mathematical, so the block diagram, again, is also this one. So this is the opposite of the decimation. So the decimation, we have the anti-aliasing first, and then the sampling rate compressor, or the circuit that lowers the sampling rate. In the case of interpolation, we subject the signal first to the sampling rate expander, or the circuit that increases the sampling rate, and then we subject it to anti-imaging filter. Okay, so interpolation works by inserting L minus 1 zero-valued samples for each input sample. The sampling rate therefore increases from f of s to L times f of s. The expansion process is followed by a unique digital low-pass filter called an anti-imaging filter. Although the expansion process does not cause aliasing since the sample frequency is very high, it does, however, yield undesirable replicas in the signal's frequency spectrum. Okay. So the problem with interpolation is imaging. So we subject it to anti-imaging filters. The problem with decimation is anti-aliasing because of the lower sampling rate. So we subject it to anti-aliasing filter. So frequency transforms of decimated and expanded sequences. So the analysis of decimation and expansion is better understood by assessing their respective frequency spectrums using the Fourier transform. So we have here our original signal, and this is the interpolated signal. Okay. Okay, so we have our original signal here. Let's say this is the original signal because this is decimation. This one is expansion or interpolation. Okay, so let's say this is our original signal, x of n, and we have other samples here. And this is our decimated signal. Okay, So this is the original Fourier transform of our signal, or the Fourier transform of the original signal. Again, Fourier transform is the transformation from time domain to frequency domain. Okay. So again, this is the Fourier transform of the original signal. We subject the original signal to low pass filtering. Low pass filtering again filters the low frequency and then allows the set frequency and above to pass. Right? In this case, this is the set frequency. So all the frequency below this line will be filtered. So this is what is left. Okay. Then this signal will be decimated as to the block diagram of our decimation earlier. So we subject it first to anti-aliasing or low pass filtering, and then we decimate the signal. Okay, so this is the original signal, this is the signal after the low pass filtering, and then this is the signal after decimation. So this is the Fourier transform representation. Next, we have the Fourier transform representation of our interpolated signal. Okay, so the effect of expansion on a signal in the frequency domain is illustrated in the figure. Remember the block diagram for interpolation. So first, we subject the original signal to sample rate expander, then we apply anti-imaging, okay, filter. In this case, this is our original signal. We multiply it by a factor L. For example, L is 3. Okay, so we see 3 replicas of our original signal. Okay, because L is 3. Then, anti-imaging filter, it will filter out the replicas. Okay, so this is our original signal now. These are replicas, so they will be filtered out. So this is the signal after the interpolation. So again, this is the Fourier transform representation. Okay, let's proceed. So sampling rate conversion. A common use of multi-rate signal processing for sampling rate conversion. Suppose a digital signal x of n is sampled at an interval t1, and we wish to obtain a signal y of n at an interval t2. Then the techniques of decimation and interpolation enable this operation, providing the ratio t1 over t2 is a rational number. Sampling rate conversion can be accomplished by L-fold expansion, followed by low-pass filtering, and then M-fold decimation. It is important to emphasize that the interpolation should be performed first and decimation second to preserve the desired spectral characteristics of x of n. Furthermore, by cascading the two in this manner, both of the filters can be combined into one single low-pass filter. So let's discuss the block diagram of our sampling rate conversion. So from our signal x of n, okay, so we interpolate the signal first, multiply it by factor of L or L-fold expansion, then we subject it to low-pass filter, and then we apply M-fold decimation. So why it should be in this order? Why should we expand or interpolate first, then filter, then M-fold decimation? Remember the block diagram of interpolation. Okay, so for the block diagram of interpolation, it was L, then anti-imaging filter. So x of n, then L, then filter, then y of n. In the case of decimation, that was x of n, then filter, then decimate, then y of n. Okay, so as we can see, the common factor between interpolation and decimation is the filter. Okay, that's why combining the two, we have the filter in between. And we always start with interpolation. Why? Because if we start with decimation, for example, we have our signal here, decimating the signal first will lose its quality. Okay, because of the lower sampling rate. The information will be not necessarily destroyed, but the quality will not be recovered as accurate as possible. Okay, so if we do decimation first, quality destroyed, then we do filtering, then we do sampling rate expander. So no matter how high the sampling rate applied by our interpolation, okay, so whatever is left after decimation will only be the quality that will be interpolated. So if the quality after decimation is already low, no matter how high the interpolation will be, the quality will not be the same as the original. That's why the first step is always to interpolate. Okay, so that the quality of the original signal will be preserved, and then after decimation, at least the decimation process will be of a signal that is still as accurate as the original signal. So that's why it should be always in this order: expansion first, filtering second, and then decimation. Okay. So an example of sampling rate conversion will take place from when a song from a DVD or CD, for example, is transferred into digital audio. So the sampling rate usually will be increased because the sampling rate on physical media like CD or DVD is limited, unlike on digital audio that we can have as high sampling rate as possible. So in this case, the sampling rate will be increased from 44.1 kilohertz from the CD to 48 kilohertz to the digital format. To enable this process, okay, so we will subject it to sampling rate converter. Okay. Notice that when we download audio from our or from the internet, usually we have choices to choose onto what sampling rate the digital file or the audio file will be. Okay. I think the most common on this one smartphones nowadays is 128 kilohertz sample when we download audio files. Lower than that is noticeably of low quality. Okay. Next, we have multi-stage approach. So when the sampling rate changes are large, it is often better to perform the operation in multiple stages, where m sub I, l sub I, and integer is the factor for the stage I. Okay, so I is the stage. Here we have an example of a multi-stage approach for decimation. The multi-stage approach allows a significant relaxation of the anti-alias and anti-imaging filters with a consequent reduction in the filter complexity. The optimum number of stages is one that leads to the least computational effort in terms of either the multiplications per second or the total storage requirement. So this is how a multi-stage approach is executed. So we have our original signal, one sample rate converter, then another sample rate converter, then another, and until we get, or the optimum number of stages to get the desired sample rate for our signal. Okay. Notice that the stage is complete. So we have L1, then the filter, then M1. Second stage, L2, then the filter, then M2, and so on and so forth. So that's it for our multi-stage approach. Next, we have polyphase filters. So potential computational savings can be made within the process of decimation, interpolation, and sampling rate conversion. Polyphase filters is the name given to certain realizations of multi-rate filtering operations, which facilitate computational savings on both hardware and software. So an example, the combined low-pass filter and the sampling rate converter as illustrated in this figure. Okay. So we have here our, what to call this one, interpolation. So L-fold expansion and then M-fold decimation. These are low-pass filters. Okay. So inverter. So instead of a simple sampling rate conversion wherein we have the L-fold expansion, then the filter, and then the M-fold expansion, what happens here is the signal is subjected to polyphase or many phases of filtering. Okay, so this is the signal filtered, the same signal inverted and filtered, same signal inverted and filtered, same signal then filtered. Then these filtered signals are added using the adder function or the adder circuit. Then the output will then be decimated. Then it will be y of n. Okay. So in principle, the simplest realization of the low-pass filter is the direct form FIR structure. However, this type of structure is very inefficient owing to the interpolation process, which introduces L-1 zeros between consecutive points in the signal. If L is large, then the majority of the signal components fed into the FIR filter is 0. As a result, most of the multiplications and additions are 0, many pointless calculations. Furthermore, the decimation process itself implies that only 1 out of every M output samples is required at the output of the sampling rate converter. Consequently, only 1 out of every M possible values at the output filter needs to be computed. This type of structure, therefore, leads to much inefficiency during the process of sampling rate conversion. So a more efficient realization structure of the sampling rate converter uses polyphase filters. So it takes into account that after the interpolation process, the signal consists of L-10 coefficients, and the decimation process implies that only 1 out of every M samples is required at the output of the converter. To make the scheme more efficient, low-pass filter is replaced by a bank of filters arranged in parallel as illustrated in the diagram. The sampling rate conversion process is undertaken by the multiplexer at the output by selecting every MT over L samples. In this example, the efficient realization is illustrated for a signal which is shown in the diagram. Okay. So again, because of the because of the many zeros added, so the term for the samples in between the original samples of our interpolation. This one. Okay, so remember this is our original signal interpolated times 3, so we have 3 signals instead of 1. And then these 2 additional signals, which was not on the original signal, are called zeros. Okay, so because of these multiple zeros, so we need, or rather, this approach is prone to errors because the filter can, or the low pass filter can only do so much. And this polyphase filters, or the purpose of this polyphase filters is to deal with every zeros of the interpolated signal. Okay. So applications of multi-rate digital signal processing. One other attractive feature about oversampling is the effect of reducing the noise power spectral density by spreading the noise power over a large bandwidth. This is illustrated in the figure and mathematical definition below. So noise power spectral density is equals to total power divided by bandwidth. So as a consequence, the reduction in the noise power spectral density, it means that the level of tolerable noise can be increased by a factor of 8. In terms of the quantization noise power Q sub 2, it means that it can now mean, it can be 8 times greater, or the quantization step size Q can be increased by square root of 8. This ultimately, or this is Q squared. This ultimately means that the reduction in the number of bits for the digital to analog converter is possible. In general, the reduction in the number of bits for the DAC process is given by the equation below. Okay. So multi-rate systems are used in a CD player when the music signal is converted from digital to analog. Digital data are read from the disk at a sampling rate of 44.1 kHz. If this data were converted directly into an analog signal, image frequency bands centered on multiples of the sampling rate would occur, causing amplifier overload and distortion in the music signal. Okay, so to protect against this, a common technique called oversampling is often implemented nowadays in all CD players and in most digital processing systems of music signal. So figure 9.11 below illustrates a basic block diagram of a CD player and how oversampling is utilized. Okay, so this is our disk. Then this is the digital processing. The sampling rate is 44.1 kilohertz. Okay. Then the digital audio will be oversampled by a factor of 8 or L times 8 to 352.8 kilohertz because this is the 44.1 kilohertz is very low for our speakers. Okay, for our digital to analog converters. So if we will directly use the 44.1 kilohertz audio to our digital to analog converters, then to our speakers, so the music signal will be distorted. That's why sample rate converters is important when dealing with signals. Okay, so that's it. So that's the end of our week number 13 discussion, which is multi-rate digital signal processing.